So okay. All right. So I want to go first to the materials that we've had in the past already. Big bunch of stuff that you've got to stare at, and I'm going to stare at it now myself. The thing I've got up on the screen right now is a little bit into the notes, page 9, and it's important because what we all know something about is limits of real valued functions of one real variable, and this is not exactly that, but it's closer to it. This is real valued functions of a vector variable, whereas what you're trying to find a limit over here, the thing we're trying to do in this problem is to find the limit as x is a vector and f of x goes into several dimensions. And the point is you don't have to worry about the several dimensions. What you do is break the function up into its components, and you have to worry about the x being a vector, but you don't have to worry about the answer being a vector. So in that epsilon delta definition, which we're not going to be dealing with except every once in a while, but in that definition, the f of fk has to get close to lk. That means a number. So this is absolute value when you take the difference here. Okay. Now, the vector is a norm. You have to take the difference of norms. So when you say x gets close to x naught, that's in a norm. That's a square root of a sum of squares thing. But if you do these, you have to do m of them. But if you do these, you're talking about getting close in a real number sense. So it's considered to be much easier to do m of these than to try to do one of these. Now, it's equivalent because that's what you do. So what the proof here is trying to prove that if you know this, then you know these over here. If you know all these over here, then you know this. And so what you have to do in the proof is put together the epsilon delta definition for vector valued functions of a vector variable together with m real valued function epsilon and delta things. And so it's a little bit complicated because you have a whole bunch of different things you're assuming, but the result is something we're going to need to use a lot. Now, the second one says if you don't want to talk about f of x going to a, instead you can talk about the difference going to 0. Okay, and that turns out to be a trick we use occasionally. You got anybody else coming in here? Nobody else coming at the moment. Okay, and this next one is difficult in a sense of how it reads just because of how you have to set it up. But let's talk about what it's trying to say. It's trying to say that instead of x heading to x naught, we can instead have x naught plus h here and let the h go to 0. When I have the sum of two things, but this one is going to 0, then x naught plus h is approaching x naught. So you have this in Calc 1. When we talk about limits of a difference quotient, you can talk about f of x minus f of x naught over x minus x naught. As x goes to x naught, that's the definition of a derivative. Or you can talk about f of x naught plus h minus f of x naught over h as h goes to 0. So you're used to this. All we're doing in vector form is saying it's the same idea. When you add two vectors and let this vector approach 0, you are basically having x approach x naught. And so the limit is the same. This allows us, when we see something, to go from one way of doing it to the other. And for example, you may remember when we proved the sine function was continuous at 0. In order to do that, we needed to switch over to the h going to 0 instead of what the sign was doing. And the reason we needed to do that is because we needed at that time to do a sine of x naught plus h. That allowed us to replace that with sine of x naught cosine h and cosine x naught sine h. You may remember that formula. Anyway, we needed to go to that in order to deal with the transcendental function called the sine function. We didn't need to do that when we were talking just about the algebra problems. But anyway, you have the same facility in vectors as we had that you're used to in real numbers. Now, something we didn't have before is this one. This one says, I want to talk about a limit. I have a limit as x goes to x naught. I want to find out whether I have a limit. Now, what's this one up here say? This says f of x naught plus tv. Now, x naught plus tv from section 12.5 should be familiar to you. It's a straight line. So what we're saying is, if when x gets close to x naught, f of x gets close to y naught, then if you approach x naught on a line, that you ought to get the same limit. In other words, if the limit when you get close is something, then approaching on lines to that limit should give you the same answer. Now, this is useful to show a function does not have a limit someplace. In other words, if you approach x naught, if you approach the center of something, you're heading toward like the center of town, okay? And if approaching on one street gives you a different answer than approaching on another street, then there's no limit in general. Now, just to try to give you something, I don't know if it's very relevant or not, but a rough analogy, there are lots of, let's say, people in Wichita of one ethnic background in certain parts of the city. Now, we have people, of course, of all backgrounds, all races, creeds, colors, and so forth, all over the city. But traditionally, historically, towns used to be divided up, like New York City used to have an Italian area, and they used to have a Chinese area, and so on, because people, when they first come to the country, tend to accumulate in areas where there are other people that they view to be like them. Okay, now this is not trying to do something deep in any kind of way to make anybody upset, I hope. But the point is, if you drive into Wichita on certain streets, you will see a lot of a certain ethnic group as you drive down the street. And you might decide, if that's what you think, that the whole city is composed of a certain kind of people. I don't know what kind of people even means. I hope you're understanding what I'm trying to say here. You don't want to make a conclusion about a limit, about where you're going, by heading in on one line and trying to decide what happens if you approach on one line only. You need to approach everything close enough in a circle, in 2 dimensions, in a circle. So as soon as you get within a certain distance of the center, then everything ought to start looking alike. Okay, if there's a limit. We're going to talk about doing problems here about this, but this particular little proposition is trying to say, don't believe everything you see if you only approach on one line. You have to approach in every different direction to be able to talk about a limit. So that's what that is. And then at the bottom here, this before, because we have to do continuity next, but before that, we talk about limits at infinity. And what that does is that takes the epsilon delta definition and it only changes the then part of the if-then statement. If I'm saying the function is going to infinity, then it's bigger than any positive number. And in this particular case, notice that this is a real valued function, because when as soon as we bring in greater than, we're talking about real numbers. The x is a vector, but f of x is a real number. What we're saying is, And we usually think of epsilon in limits as small, but when you're talking about infinity, you think of epsilon as large. So we're saying you pick a large number, then I've got to find an x which is close to x naught, but its function value is bigger than your large number. And if you can do that, no matter how large the number is, then we say the limit's infinity. If you can do that, no matter how large you get, so that the value is less than minus that, now we're talking about getting very negative. That's when you have minus infinity. So we have infinite things in these kind of functions where the vector x is not a real x. These x's should have, this is a typo, should be heavy print. They will be later when I correct this. But anyway, these should be heavy print like these. But basically we have infinite limits as well. And then we talk about continuity. Now, all continuity is telling you what the limit is if you assume the function is continuous. And so the problem with limits, doing limits, is you have to figure out what you think the limit is before you do any kind of proofs, before you verify. With continuity, it tells you what the limit might, if there is one, what it is. And namely, you evaluate the function at the point that you are heading toward. Now, that means two things. One, if you're talking about continuity at x naught, the function has to be defined at x naught. So you have to have f of x naught. If x naught's not in the domain, the function's not continuous there. Okay. Now, this is a definition when we have real valued functions. This is the way it looks. Down here, this is the way it looks for vector valued functions. And except for the bold print, I hope you see it's the same thing. Now, this first statement up here may be a little bit cryptical because maybe you don't remember what this is. We use d prime to mean accumulation points. So in order to take limits, the point you are taking the limit at, which is bad grammar, but the point at which you are taking the limit, better grammar, has to be an accumulation point. However, for continuity, you don't have to have an accumulation point. If the function's just defined at an isolated point for the function, for the domain, the function's automatically continuous. So if I have a function and the domain is a finite set, so the graph would be a finite number of points, no continuous thing passing through the points, just finite number of points. That is a continuous function. So 4 dots on a page would be a continuous function if you have a function set up, because all those points are isolated. Now, the textbook you have does not discover that because they don't talk about it. For the textbook, the points they take to be x naught are always going to be interior points of a set. So the author doesn't discuss isolated points, and therefore, for the author, the limit is what guarantees continuity, because if you have an accumulation point, then you have the limit, and the limit has to be equal to the function value. So continuity is easier than limits because you know what limit you're trying to show is the limit of the function. So that means all the theorems in the 11 pages above here, page 12 is what we're on here, all the theorems in up to page 12 are true already for continuity, because all you do in this stuff is replace the limit in the first 11 pages with the function value. That's why I said all the limits become continuity theorems. More precisely, if it can be, it is this: if it's assumed the functions mentioned below are continuous, then the sum of continuous functions is continuous. The multiplication by a number for continuous functions are continuous. And what I said here, if you now know what a vector space is, continuous functions form a vector space of functions. Now, what was the thing about vector spaces? They were, addition was commutative and associative, and there was an identity element, and everybody had an inverse. Also, you could multiply by scalars, and you could distribute to scalars and stuff. Those were the axioms in a vector space. So just by saying this, I know lots of stuff about continuous functions without proving anything. Okay. I even bring in complex numbers here. You don't have to worry about that, but it's true for complex numbers as well. Okay. Now, when you take things like reciprocals, you have to be careful because you can't divide by a vector. So these have to be real valued functions. That's why I say real valued function here. But a reciprocal of a continuous is continuous. Now, what about the places where the denominator becomes 0? Well, the point is that that's not in the domain. If it's not in the domain, then we don't talk about it. Okay, so all the places where it is in the where the x naught is in the domain, the function is continuous. And here, vector space is function is continuous if and only if each of its components is continuous. That's the first thing I started out with this morning. And I think as I talk here, I'm going to take your snapshot of the ones of us who are here today, and let's do that real quick. So you're now immortalized. We can go on here. Okay. Now, the one extra thing, and not extra, but the one you didn't have in the limits, because it's very complicated to state, but for continuous functions, it's easy. Namely, the composition of continuous functions is a continuous function. So if I have a function given by sine of x squared in real numbers, because x squared gives you a continuous function, because sine gives you a continuous function, the composition is continuous. So these things are meant to, when you stare at a function's formula, to immediately tell you whether it's continuous or not. That's the purpose of them. And so I think at the moment, that's all I want to say about this. The stuff underneath here is more technical stuff having to do with open sets. And for a continuous function, the inverse image of open set is open. We don't really need to worry about that yet, because that is what we use in higher level mathematics to talk about continuity when we don't have vector spaces. When we don't have distances. So there's continuity definitions in a much more general sense, but you and I aren't going to have to worry about that very much. So I included that in here. And there's some other stuff in here about sets and so forth that are open, and continuity preserves limits of sequences. Talk 2, we talked about limits of sequences. So the rest of this stuff from about 15 on, you basically don't need to worry about until you get to the next chapter, which starts on essentially page 17. So last 2 or 3 pages in here, you don't need to worry about so much. But I would like you to realize that all we've been trying to do is to generalize everything you knew from Calc 1 about limits and show you what things are still true about functions of several variables. That's why I wanted to do it first. And that's why really we're kind of in chapter 14, because that's where the author talks about it. To me, chapter 13 is a part of the function we've been talking about. In chapter 13, the domain is real and the range is vector. But in general, the domain is vector and the range is vector. So 13 is part of the general concepts, and that's why I wanted to give it to you to start with. So I'm going to stop that share, so you're going to see my ugly face and so forth. And I need a haircut. Hopefully tomorrow or Friday when you see me, I will be different looking. Probably haven't caught the virus from the barber, but I hope to have some of these beautiful locks changed. Anyway, what I'd like to do, I think now, is go to WebAssign. And so that gets over to a different place. You see me going over here to a different camera. I put some WebAssign problems on yesterday. I thought we ought to talk about them a little bit because in this honors class, for those of you guys who haven't been with me before, I'm interested in your learning, and I'm not so concerned with how many points you accumulate because, let's see, I'm seeing how it comes out here on the screen. I think that's readable except for some reason. Okay. You guys can all see the problems one and stuff. Now, I've decided this year I look at things usually in the exercises that are available to us. There are some videos, and videos are unfortunately are, if you see this now, this is the author of the book. Unfortunately, he is no longer with us in the world, but he explains lots of different things, and he seemed to like to put videos on here of himself explaining some of the concepts. So this gives you a second exposure to somebody else, and I think it's a nice idea for you to see other people besides me. So anyway, they always ask a question at the end of watching this, in this case, a minute and 54-second video. They ask you this question. Now, what they say is, watch the video, then answer the question. Well, I would answer the question and then watch the video because you want to see if you're right. Okay. Now, you guys get 3 chances at these questions, and this is a true-false question. So if you miss it with 3 chances, I suggest maybe you're in the wrong class. Okay. In any event, let's look at the question, not the video. What you have here is a function. When I stare at it, I see, first of all, 2 variables. That's the domain. Look over here, because he's not telling me domain and range, because that's what authors do. That's dumb, in my opinion, but that's what authors do. They should tell you, but they think you're smart enough to figure it out. Well, and what is on the right-hand side here? X times e to the x squared times y. Not a very pretty little thing over here, but what are you supposed to do with it? First of all, this is a real valued function because the stuff on the right is a bunch of numbers multiplied together. So you're starting with 2 variables. This is a real valued function of 2 real variables. Now remember, in chapter 14, every function the author talks about is a real valued function. So that's no surprise if you know what 14 is about. What in the world is this over here? This is a partial derivative. Well, we haven't talked about partial derivatives yet in here. So right away, well, that's what the video is about. Now, we have so far talked about limits and continuity. The next concept is going to be differentiability. Okay, that's like section 3 in chapter 14. So this problem is really out of place. But since it's here, I thought I would leave it in. Let's just talk about it. What do we mean by a partial derivative? Now, no theory, nothing else that we're going to do. It just means treat everybody except x, and that means y in this problem, as a constant and differentiate. So if y is a constant, like 3 or something, and I saw this thing where I don't worry about what y is, it's just a constant, and I differentiate with respect to x, then all I'm really worried about is this part here. Okay, and evidently we'd have to have a product rule to do that. We're just not paying attention to y. Okay. So now when I look at this, I'm not even sure that's right. Because you think the y
that's why it's false.
I know, but I haven't got to you're way ahead of me. See, you've already looked at the answer, but you're not supposed to. So like, something's wrong here. So now I would never have this problem here myself because it's problem 1. in a new exercise set, and it doesn't make any sense. I don't think that's very good pedagogy. But anyway, when you look at this, it's like, this doesn't make any sense. So I assume you choose false, okay? But if you watch the brilliant presentation, I assume that will tell you what to choose. Anyway, this is never, these problems are always true, false. This shouldn't slow you down very much, no matter how many problems you're supposed to do. And if you look here, this says my assignment I gave you is going to take 250 minutes. That's over 4 hours. I'm sorry about that. But one of the things I learned about these things is every once in a while you find the problem and it says it's going to take 2 hours to do, and that's just a typo. So sometimes these numbers are not real, in the sense that you might have a thing you can do in 2 minutes and it says it's going to take 4 hours. Well, don't believe it. So I'm not trying to make you work for 4 hours. So that's why you get to choose. And so what I said here is writing some of these, working these exercises, really working on all of them, will help you visualize three-dimensional graphs and the function to produce them. Do as many problems as you need, okay? Now, if later I look at this list and see that you have not done it, not done anything, then you better have a pretty good result on the test over it. In other words, I will take your lack of doing it to mean you know what you're doing. I'm going to deduct your grades later if you don't do homework and we find out that you don't know what you're doing. So if you can show me you don't need to do the problems, you don't need to do them. The idea here is to get away from worrying about grades and worry about knowledge. So let's talk about these particular things here. This is problem 2. Just real quick, what are you supposed to see here now? Well, again, they're all real valued. I see a cosine and I see an inside. This is a composite. A composite. Okay. So if we would independently talk about the continuity of this, which we can, and independently talk about the continuity of cosine, then we just talked a while ago about the composition of continuous functions being continuous. Okay. Now, in this question, however, if you read the question, they're not asking about that. They're just saying evaluate. So where we are is at the very beginning. They want to know, can you get the right answer if you stick 4 and minus 1 into the problem? Okay. Well, if you do that, what do you get? You get x is 4, so I'm going to get 4, and y is minus 1. I'm going to get 0 here. So I need to know what the cosine of 0 is. If that's too much for you, you shouldn't be in the class. If you know the cosine of 0 is 1, you'll know, whoa, here's a good answer. Hopefully you would have put that there. So find the domain. The domain's everything that makes sense. The cosine always makes sense. X plus 4y always makes sense. So what are you supposed to write here? R2. Except you don't have to write it, you just have to choose it. This says the x and y is between minus pi over 2 and stuff, but cosine is defined everywhere. This one tries to play games with the ranges and stuff, with minus 4 and stuff. That's just nonsense. Same way with this. That's not, this stuff here is just nonsense. Hopefully, if you look here, you say, okay, under what conditions does x plus 4y make sense? The answer is everywhere, cosine everywhere, domain everywhere. What's the range though? The range is going to be dependent on this last function. How big does cosine ever get? 1. Anyway, you see the answer. So hopefully this is an easy problem. Should it take you 3 minutes? I don't know. I think it might take you a minute to read it, but then I think you ought to be able to say, oh, that's just 0, that's 1. So to me, it's a 15-second problem. Okay, now, these kind of problems are good because it makes you think about the domain, okay? Where's the logarithm makes sense? Only if the numbers are positive. So what do you have to have in here? You have to have the stuff in here be positive. So what I would do is separately write out 16 minus x squared minus 16y squared is some number, like 5 or something. It has to be positive and see what you've got. And when you work that out, you will see that you get a what should have been done in Calc 2, you get an ellipse. And that's why the first number is checked here. Now, you get an ellipse here, you get an ellipse there. Which one is it? Well, for ellipses, if you remember, they look like x squared over a squared plus y squared over b squared. I'm doing this in my head here with the arrow, equals a positive number. And it's the size of the denominators that tell you whether it looks this way or this way. So now, I don't care if you get this right or not really, except this ought to cause you to think about reviewing what you know about these kind of functions of two variables that are ellipses, hyperbolas, or circles, or parabolas. So what did he do here? He gave you half of a parabola. I'm not sure what this is. I guess this is putting in all the logarithm stuff if you just had a log. But basically, what you're supposed to think out here is the inside makes an ellipse. So it's one of these two pictures. Anyway, but all this is meant to do is to help you do your thinking about such functions. We're going to consider this picture, the correct one, to be on the floor of our surface that we study, because the domain is going to be two-dimensional, and it'll be an ellipse in this problem, and the range is going to be what this function equals, and that will be a surface. So this is not the graph of the function, this is the graph of the domain of the function. So he gives you some problems like that. He gives you something like this. Where does this not make sense when the denominator is 0? The denominator is going to be 0 on this line right here. So this is the one to pick. I know that because I have the answer already picked for me. Anyway, so he gives you some pictures, some problems, and then we get down to this kind of thing. So on this one, he gives you a tutorial. Now, when I see this, I think of two things. All we're supposed to do is domains here. You can't have something where the denominator is 0, so x can't be plus or 2 or minus 2. So I'm going to throw away x is plus 2 and minus 2. What does that mean on the floor? If the floor is the xy axis, what does that mean? That means you're not going to have two vertical lines in the graph. Namely, you're not going to have x equals 2, and you're not going to have x equals minus 2 in the graph. So you're going to have to erase two lines from the domain wherever they hit the domain. What about the numerator? Well, if I look at the inside, always look inside, this is a parabola shape. And square roots only make sense if this is positive. So I'm going to either have the inside of a parabola or the outside of a parabola, depending on what I have to think. In this particular case, I don't know, but if I sneak a peek down here, we've got some answers down here. Now, do parabolas look like this or do they look like that? Well, both. But if y is x squared, does it look like this? Or does it look like this? And I think you know, if y is x squared, it looks like one of these. Now, what did I throw away? I threw away the vertical lines already. So this is so far so good. This throws away 4. This throws away 2. I already figured that out. So now, of course, I know the answer. But this is why the answer, because you're throwing away 2. You're not throwing away 4. 4 would be what you threw away if you had x here. Now, some of you might sound out, is this worth doing or do you want me to skip this stuff? Nobody wants to say anything? Okay. Well, we get a little more complicated because now we have a three-dimensional domain. Now, for this, we're not going to, oh, somebody's, what is it, from Peyton? I think this is worth going over. Thank you, Peyton. I wish you guys would unmute yourself for a minute because I'm not looking at those screens where this chat is. But anyway, now we have three-dimensional domains, and we haven't really studied those. That's why I'd pay more attention to these. Again, the log, I'm not worried so much about the log at the beginning. I'm worried about what in the world this is. Well, this is the last section of chapter 12, where you talk about these kind of things. So you might have to go back to chapter 12, open your book, and look around and see what kind of pictures you got there. This is a cylinder. This is an ellipsoid. This looks like some kind of parabola with a circle or an ellipse. So there's names for that. So what's he going to ask you about? Find and sketch the domain. So you're going to have to do this on your own, so I would never see it. He says this is the right answer. And that's because if you would set the inside here to equal some positive number, then notice that the x squared, the y squared, and the z squared are all the same sign. That's where you get an ellipse idea. The ellipsoid comes up in chapter 12, where we're doing that thing about three-dimensional domains in 12.5. I haven't hit very hard yet. I just put some problems for you to do upon request, but we haven't hit it yet. But we're going to be doing it all semester, okay? And so when I get back either to Blackboard or when we get to writing on a piece of paper here, not looking at this web assign, I can actually show you, write this thing out and show you that it looks like an ellipsoid, because it's going to be like 9x squared plus 4x squared plus z squared equals something. In this case, 36, but it'll be 36 plus something, okay? And that, if we go back to chapter 12, we'll see it's an ellipse. Anyway, this is the answer to this problem. Now what I got here is I got some cone shapes. This looks to me like a parabolic shape with a circle. I have a cone idea, straight lines. I've got some cylinders here. So let's see what this is. Okay, f of xy is x squared. There's no y over here. Okay, y didn't show up today. So like a couple of students. So everything's going to depend on the x. So if I would fix a y, so that means here's the y-axis. I don't know that this is correct. The author says it's incorrect. I don't care. Right now, if I would fix a y, I go out here a certain distance, I ought to have at that distance out a parabola with, for x's, it ought to be when x is 1, I ought to get 1. When x is 2, I ought to get 4 and stuff. And so I ought to get a parabolic shape, because what we're going to do is set this equal to z. So z is going to be x squared. In other words, the height is going to involve the x squared. So if I would fix a y out here, I ought to get a parabola between x and z. Well, here's a parabola between x and z. Here's a parabola between y and z. This is wrong. It's going to be a parabola between x and z. Now, the book drew the parabola when the y is 0. I'm drawing a parabola when the y is 2, you see? So I would draw this parabola. The book drew this one because they assumed y was 0. What you need to do in the graph is put together an infinite number of parabolas that all look like these. That's how you get this cylinder. Now this stuff down here, this involves y changing as is x and so on. So these are just, I wouldn't even, I would put those aside pretty fast. Okay, what's this one? This one, the right-hand side is sort of linear, straight lines. That's why, hey, I get triangles. I don't know about that one. These are all ovals. I think without knowing anything, I go for this one, because this is about straight lines. Now, from section 12.4, if I would set this equal to z, z equals 18 minus 4x minus 5y, what do you get? You get a plane. Which one of these looks like a plane? Two of them. This doesn't look like a plane, and that doesn't look like a plane. But I don't know, where's the circle come from? I don't know. This looks like a plane to me. So it only shows you a triangle, but that's because you're only looking in the first quadrant here. Actually, this is a plane shape, not a triangular shape. If I set z equal to that, that's what you always do, set z equal to these things, and you will get a plane in this problem. So this is the obvious answer. Oh. All right. In this one, I got the sine of x. So I got my carpet. I have cheap carpet. It looks like this. My wife said today my shirt I'm wearing looks like this, but you guys probably haven't noticed, especially when you can't see me. Notice the absence of y here again. So if z equals sine x, I need to have some sine graphs between x and z. Well, this is a sine graph between x and y. Here. This is a sine graph between x and z. And the y is not mentioned, so you're going to get a cylinder again. This is going to be this answer. This is something between x and y. And I'm not sure about this one. Anyway, we can look at those. So we have a bunch of pictures in this set. Then they get pretty. And some of these might be hard for you. But it's okay, you learn. The whole idea is stare at these a while and say, okay, which one's which? And this might take a while, so let's see what they say. They say it takes you 5 minutes. Well, but you can gain some experience by playing around and seeing, what does this one look like? This one, the denominator is going to, as x and y get big, we're going to go to 0 in the denominator. So is it going to be this one? I don't think so. In this case, the z is getting big. I want the z to get small. I want to set this equal to z. And as x and y get big, this is going to go to 0. So, hey, I think it might be this one. Let's see. I think it's this one. I don't know. Maybe it's this one, because this, as x and y get big, maybe it's one of these. Could it be this? See, this seems to curl back up. I don't think so. Maybe it's this one, because this seems to go to 0. So I got 3 chances here. This one, maybe, or this one for that first one. And so on. So anyway, these are a little harder just because you're not used to it. So this, now we get into the topographical stuff, level curves. You probably do know about this just from reading maps. But some of them might be harder. But you get some pictures here involving these kind of things. And just think about it. Do you think this circular thing, if this is your map and then you go and visit, do you think this would be how it looks? Looks to me like the level sets here are rectangles or squares, whereas there are circles here. I don't think that's going to work, this picture. So I think, as I said, this is just a whole bunch of pictures and stuff that this one is good for hypnotics. This is what we do. I'll have you stare at this for 10 minutes and then I'll talk to you. Okay. And maybe we can get more learning into you by me taking control of your mind. Anyway, and it'd be better if these were moving. So maybe if I did something like this. So anyway, you see this whole set of stuff is a bunch of pictures. That's what the assignment is. And I basically said, do what you need to do to learn about it. Okay, now it's 15 after. I'm hoping that going through something like that's helpful. In section 2, maybe we should look at that real quick because we're running out of time, but I have something else to talk about here. But if I go back here, hopefully, I shouldn't have gotten out so fast. Go back here and go home. That's what I'm trying to do here. And go back to your class. Yeah. Okay. If I go to 14.2, just real quick, quick as I can, expand them all. What do these look like? Well, in this case, these are both videos. Sorry, this one's a video. Doesn't matter what. But this starts out real easily and asks you questions about continuity. Things about continuity. Find the limit if it exists. And hopefully, when you go to 0 here, you'll notice that these things both go to 0, and that's a problem. And so what we've done now is left the picture format of the last section, which was almost all pictures, into doing some computations. And so we'll be talking more about this on Friday, but hopefully I left some tutorial ones in here for you. They, you know, you have to do some stuff with algebra. And what you do with limits, you know, is you try to factor if you can. Well, if you look at this thing, I don't see how to factor that. So I would be, if I can't factor it, then I got to go see what happens to the denominator, because this is a fraction. Whereas here, in this problem, again, we're running out of time, I'm composing. And if I compose, this one's always continuous. It's just a nice straight, in this case, a plane. What's this one over here? It's okay here. This has to be, the t has to be positive, but it looks to me like the composition of functions might be continuous as long as the answer here. Now we're going to take g of, so we're going to stick this formula and stick it under the square root. That means this is going to have to be positive stuff. So that's going to restrict the answer, but you get some choices here. You can sort of visualize, what does this mean? What does this mean? What does this mean? I think you, in this case, you have to pick the last one. But, and so we'll talk more about these on Friday. But these are, as you notice, going through them, because I'm running out of time, but these are all almost all computational. Now, I did leave for you guys, today I was asked to do something left in 12, so I did put the two things in 12. And I want you to know how to do equations of lines and planes. So that section 12.5, I think I gave you like a couple of weeks to do or something. Some of these things are, the problem sets due like next week after the break. Okay, so I'm going to stop the recording.